Welcome back. At this point, you've had an opportunity to go through a demonstration that was showing the electrolyte properties of strong, weak, and non-electrolytic solutions. We just wanted to make some further comments, some additional clarification as we proceed into really understanding what electrolytes are. Remember, just kind of write some side notes with me here. We have ionic compounds that we have mentioned in our first year chemistry as being those compounds that are made of a metal hooked to a nonmetal. We talked about a positive ion hooking to a negative ion. We crisscross charges to come up with an electrically neutral compound. Ionic compounds are commonly called salts. Water-soluble salts are strong electrolytes. And you'll see that if indeed a salt dissolves in water, it will 100% dissociate, forming lots of charged particles, and the light bulb will glow brightly. The other category of compound are called molecular compounds. And molecular compounds, when we take nonmetals and hook them to nonmetals in the same structure by covalent bonds, nonmetals plus nonmetals, 2-3 different elements hooked together to create a molecular compound. There is no such thing as charges. There are no ions. These tend to be non-electrolytes. So strong electrolytes versus non-electrolytes can be quickly categorized simply by denoting if it's an ionic or molecular compound. But what about that in-between category? Those types of compounds that build what we called weak electrolytes. Weak electrolytes come from molecular compounds in a very special category of molecular compounds known as weak acids. One of the last units we studied in first year chemistry was acid-base chemistry. Just a very quick definition from the Arrhenius definition, we know that acids ionize to give hydrogen ions. Acids start with an H. Any hydrogen hooked to some negative ion is a formula representing an acid. HCl, hydrochloric acid. H2SO4, sulfuric acid, and so forth. So these compounds, known as acids, now several of these acids will 100% dissociate. These will be strong electrolytes, but the vast majority, by far the majority of acids are known as weak electrolytes and only partially dissociate. So thinking this through, molecular compounds in water usually consist of intact molecules dispersed throughout that solution. Consequently, most molecular compounds are non-electrolytes. This is the term that will fill in your blank, non-electrolytes. There are, however, a few molecular substances whose aqueous solutions do indeed contain ions, and the most important of these are known as acids. Now let's proceed further with that discussion on acids. We know acids form hydrogen ions, H+. Sometimes we've called those hydrogen ions protons in the Bronsted-Lowry acid-base theory. Hydrogen ions, when released, make the solution acidic, and that's indeed what we measure on our pH scale, is the concentration of those hydrogen ions in the water. When strong acids are placed into water, strong acids indeed mean 100% dissociate. And when they do dissociate 100%, they will release their ions. Weak acids do not dissociate completely. They only partially ionize. There are 7 strong acids that we need to memorize. And I hardly say that, but this really will be so helpful to you. Because see, if we memorize the 7 strong acids, you now know all of the weak acids as well. Memorize the 7 strong electrolytic acids, and here they are. I'll write their formulas. You write them along with their names. The binary acid hydrochloric is strong. Hydrochloric acid. it will 100% dissociate when placed into water. So what the word strong means, when HCl, which is actually in a gaseous form, is placed into water to create a solution, see the acid forms after it's placed into water, 100% are going to be lying to the right of this arrow forming products. And of course these would have adjectives AQ, aqueous ions. Gaseous hydrogen chloride, when placed into water, forms an acid, hydrogen ions and chloride ions, 100% dissociation. So let's keep writing our 7 strong acids. We have HCl, another binary acid, HBr, hydrobromic acid. The third binary acid is HI, hydroiodic acid. Hydroiodic acid, HI, will 100% dissociate. We have HClO3. This is a ternary acid from the polyatomic ion chlorate. H turns to ic, and we get chloric acid. Hydrochloric, HCl, and plain old chloric, HClO3. And there's another strong acid that contains chlorine. It comes from the polyatomic ion perchlorate. So this is perchloric acid. The 6th acid that's considered strong is nitric acid. And the last one is a diprotic acid, sulfuric, from the polyatomic sulfate. We have sulfuric acid. HCl, hydrochloric. HBr, hydrobromic. HI, hydroiodic. HClO3 is chloric. HClO4, perchloric. HNO3, nitric acid, and the last one, H2SO4, sulfuric acid. 7 strong acids. Now, I need you to memorize those because now you know all of the weak ones as well. If you're looking at a formula for a weak acid and it's not one of these 7, it will only slightly turn that light bulb on, giving a partial ionization and a very dim glow on the bulb. 7 strong acids, and now we know the weak ones. Let's further this with just a little bit of an example on the top of page 3 to just clarify further what strong versus weak means. I'm going to just add a new little slide in here. To write the dissociation for hydrochloric acid, hydrochloric 100% dissociates, we're going to have all of the product lie to the right of our arrow. 100% pushes right to H plus and Cl negative. This represents a strong acid. Compare that to acetic acid, and this one was shown in our little video a moment ago where it slightly turned on the bulb, just a dim glow of that light bulb. Truth be known is only about 1% of the molecular form of your acid is able to separate into the ions. That's not very many, is it? That about 99% lies in the molecular form, and here you have the ionic form. So you can see an electrolyte is truly defined as the more and more and more ions that are floating in the water, the brighter the bulb is going to glow. A very weak acid, such as vinegar, and this is what acetic acid is vinegar. If I place that into water, very few ions are going to form. So if they're mostly in the molecular form, we're going to have a very slight glow, a weak electrolyte. Give it some thought with me. What are the dissolved species in the following solutions? And this is really going to help us in the nomenclature part. So I'm glad that your summer assignment had you practice nomenclature. If we give it some thought, What are the species that lie in KCN? First of all, let's begin. Is it ionic or molecular? Well, I notice it's a metal to a polyatomic group of nonmetals. Potassium is that ion K plus 1. CN, carrying a -1, is called cyanide, right off of our polyatomic ion chart. Potassium cyanide, as a solid, will indeed dissolve into water. It is water soluble, and 100% of salts will dissociate into their ions, the aqueous ion of potassium and the aqueous ion of cyanide. Now friends, remember, ions only exist in water solutions. Without the water, potassium cyanide is a white solid salt. When dissolved into water, it indeed dissolves and 100% separates into their ions. So what are the species present? Well, the species are potassium ions and cyanide ions. How about NaClO4? NaClO4. And again, this starts as a solid. I notice it's ionic, a metal hooked to a polyatomic ion group of nonmetals. Sodium carries a +1 charge. The polyatomic ion ClO4 negative is called perchlorate. As a solid, this would not conduct electricity. There's nothing to move the ions around. But when I place it into water, those ions 100% separate, giving me the positive ion of sodium in the aqueous solution and the negative ion perchlorate in the aqueous form. Sodium ions and perchlorate ions separate, and we would see a light bulb turn on when dissolved in water. Without the water, no electricity flows. But in the water, these ions separate and complete circuits. What would the dissociation equation for ammonium phosphate look like? Our compound of ammonium phosphate. Do you have your periodic table and polyatomic handy? Ammonium is the polyatomic ion NH4 carrying that +1 charge. Now phosphate is a polyatomic ion as well, PO4. It carries a -3 charge. So remember how we take a group of polyatomic ions by placing it inside a parenthesis to create an electrically neutral compound. The ionic compound called ammonium phosphate is indeed water soluble. Without the water, it's a white crystalline salt. Placed in the water, it will 100% separate and let go of its ions. Out come the positive ions and a negative ion. How many ammoniums? See how there's 3 of them in there? There's 3 groups of ammoniums, NH4+, aqueous ion, and 1 group of the polyatomic ion called phosphate, aqueous. Now friends, I cannot stress enough, most people, if they lose points or quiz questions or whatever might get marked wrong, it's because of this little tiny detail. Ions carry charges. Please write that in your notepad with me. Underline it a couple times and let me stress what I'm saying. Without the positive sign on ammonium or the -3 sign on the phosphate, I cannot give credit, because electrolytes must be charged in order to conduct a current. Charges flowing through water are electrolytes. If you look back up here and you do not have a +1 on your sodium or a -1 on your perchlorate, put it there, or you're going to be so mad that you get it marked wrong without those charges. Same up here. Ions carry charges. They must be there in order to earn your credit. Which solute will cause a light bulb to glow more brightly? We have some choices here. We have CH3OH versus MGBR2. Notice this is a molecular compound. It's all nonmetals grouped together. Molecular compounds, although they will dissolve in water because it is indeed polar, it is not built of ions. It will dissolve, but it is a non-electrolyte. No ions in there at all. Magnesium bromide we recognize as an ionic compound, metal to nonmetal. When magnesium bromide gets placed into water, it will be a very strong electrolyte, simply because I'm going to make a magnesium ion and we're going to let go of 2 bromide ions. Notice how I'm putting the charges there. There's 3 ions formed from every little crystalline solid here. Lots to turn on the bulb and let it glow brightly. Methanol, no glow, and then magnesium bromide indeed will glow brightly. We have a little drawing exercise as part of this final lesson on electrolytes. Let's take a peek. I'm going to give myself a little more room here. For instance, we want to draw a diagram that represents aqueous solutions of each of the following ionic compounds. Make each drawing contain 6 cations and then the appropriate number of anions. Make the charge of the ion relative to its size. So let's model what this is saying. The only parameter is we have to have 6 positive ions and then the appropriate number of matching negative ions. First one in the box says it's nickel, Roman numeral 2, sulfate. So let's turn that into a formula. Nickel, Roman numeral 2, tells me it's a +2. Sulfate, polyatomic ion, carries a -2. So we have 1 unit of a +2 electrically balanced with 1 unit of a -2, NiSO4. So if I have 1 nickel, I need 1 sulfate. If I have 6 nickels, I'll need 6 sulfates. And notice that the magnitude of the charge indeed is the same. Both are carrying the same charge. They're going to be the same size model. I'll use green to represent the nickel. And I'll just put that as a +2, 2, 3, I'm just randomly placing them, 4, 5, 6. 6 units of a +2. I'll use blue to represent the negative ions, and they're just going to be separated. So I'll place one here, 1, 2, 3, likes would repel, so 4, 5, 6. This represents a random dispersion of the separated nickel ions from the sulfate ions. Let's try another. How about calcium nitrate? Calcium with its +2, nitrate is a -1. So when I write my formula, I need twice the number of negative ions, 2 units of the negative nitrate, to electrically balance the calcium. So I'll use red this time. Now calcium is a +2, so I want to make it twice as large as the -1. So I have to draw 6 positives. So 1, 2, 3, 4, these are all the same size, 5, 6. If I have 1 positive, I need twice the value of negatives. So keep in mind here, 2, 4, 6, 8, 10, 12. We have a positive 12. We're going to need a total of negative 12 to give us 0. It means we're going to need 12 little circles of negative 1s. I'll make them half as big. Half the size represents half the magnitude of the charge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Calcium nitrate. Keep in mind, what we've done is saying for every 1 calcium, we had 2 nitrates, and that ratio would come out to be the perfect 1 to 2. How about sodium phosphate? Sodium phosphate. Well, let's go to work writing that formula. Sodium is a positive ion, carries a +1 charge. Phosphate is the polyatomic, carries a -3 charge. So when we crisscross, we get Na3PO4. Now keep in mind we're told to draw 6 positive ions. So I'll use blue this time, and they're going to be a +1 charge. So I'm going to do 1 sodium, +1, 2, 3, 4, 5, 6, randomly placed. Alrighty. Now how many negative ions will we need to draw? I'll put those in green. Well, you can see it only takes 1 to electrically balance 3 units of sodium. It's got to be pretty big too, because it's a -3 Na3PO4. Na3PO4, and that is sodium phosphate. So see how the same number of positives are balancing the total number of negative charges, Na3PO4. We have one more to draw together to finish off our lesson on electrolytes. Aluminum sulfate. Aluminum sulfate, well, aluminum with its +3 charge, sulfate, which carries its -2, so we have Al2, parenthesis, SO4 taken 3 times. So let's use blue to represent the +3 aluminums. We have to draw 6. So there's 1, 2, 3, 4, 5, 6. Alrighty, so that's the largest circle with its +3 charge. Now how many sulfates will we need? Remember, for every 2 aluminums, we have to draw 3 sulfates. Let's do that in red. So here's 2 aluminums. I have to draw 3 sulfates. And they're going to be -2, so I'll make them just a little bit smaller. Al2, SO4 taken 3 times. So I've got to draw 3 more here. Alrighty. And then 3 more here. And just random. That's all there is to that. If we had placed a 6, a 2 to 3 ratio, 3, 4, 5, 6, 7, 8, 9, there's a 9. 2 is to 3 is 6 is to 9. So all we've done is just represented by the size and the magnitude of the charge, and making sure that we have the same proportion that represents our subscripts. Friends, you have completed Lesson 1 from your Chapter 4. Remember, you should take a look at your assignment from the back of Chapter 4, Lesson number 1 or Assignment number 1. Criteria for credit. Remember that criteria for credit is expected on all written assignments. Write the problem out as it appears in the book, then your complete solution. Assignment number 1 goes with Lesson 1. You now have enough ammunition to practice and do well.